Good morning, everyone, and thank you for coming. My name is George. I'm a PhD student at the University of Strasbourg in France, and I'm also a senior software engineer at Atlassian in the Mill-EVOS team. I'm mostly focused on the Jitsi Videobridge and its congestion control and adaptivity features. Um, Today I'm going to present you the results from our experimental evaluation of dynamic switching between one-to-one and group video calling. So before we dive into the details, I'm going to briefly present you Jitsi Meet, which is the video conferencing system that we use to perform this measurement study. We are going to quickly go over the project and the service. First, we're going to focus on the open source stack and more specifically Jitsi Meet and the Jitsi Videobridge because these projects are the most relevant in this evaluation. Then I'm going to say a few words about our infrastructure and see a couple of metrics for our service. So here's the 10,000 foot view. The main components of the Jitsi Meet stack are the signaling node, the selective forwarding unit or SFU, in short, or Jitsi Videobridge, or simply bridge. I'm going to use all these terms interchangeably during this presentation. Um, we also have two client applications, one that runs on the web and one that runs on mobile devices. The mobile client is based on the WebRTC JavaScript APIs. These APIs were covered yesterday in Bernard Aboba's WebRTC tutorial, and the mobile client is based on React Native WebRTC and it's written in React Native, of course. For the signaling path, we use XMPP provided by Prosody, which is a flexible XMPP server written in Lua. And for the media path, we use UDP, DTLS, SRTP, and if that fails, TCP, as it is mandated by the WebRTC standard. Most of our backend is written in Java, modulo some parts that are written in C and C++. For example, we use the native SCTP library for SCTP support, and for which we have JNI bindings. So this is what Jitsi Meet looks like. This is a screenshot of one of our daily stand-ups. Here we see Jan on stage. Pavel, Boris, Christo, and other members of the team are displayed in the horizontal thumbnails bar. Jitsi Meet supports multiple layouts. We have a vertical thumbnails bar and a more recent Brady Bunch style layout. So depending on the layout and of course the available bandwidth, our SFU forwards the appropriate stream for each participant. In this specific example, Yana is being received in 720p at 30 fps resolution, whereas everybody else is received in 180p at 7.5 fps. And we also have an avatar of a participant that doesn't share his or her video. Jitsi Meet actually has many more features such as speaker stats, video quality sliders, integrated chat, Dropbox integration, transcriptions, and many other things that you're welcome to discover by browsing through our website or even better by using our service. A few words on the Jitsi Videobridge. It's a selective forwarding unit or SFU in short. It supports conferencing specific features such as simulcast and last N. So for those of you who are not very familiar with these terms, very briefly, with simulcast, an endpoint encodes and sends multiple qualities of the video stream that it is sending, and the bridge sends towards a specific receiver high quality for the on-stage participant and low quality for the thumbnails. With last N, the bridge is sending the last N active speakers instead of everybody. So our bridge also supports congestion control through adaptive simulcast and adaptive last N, so that it takes the available bandwidth into account when it computes the last N set and the specific quality to forward towards a specific receiver. The bridge has an XMPP and a REST API, so you're not required to use XMPP if you don't want to, or if you can't. We have several more open source projects, for example Gcofo, which is our signaling server, and Jibri, which is our recording tool, and you're welcome to check them out on GitHub. We also have APIs that enable you to use our service and mobile SDKs. And finally, if you're interested in learning more about any of these projects, please feel free to talk to me after this presentation is over or join our Discourse community. The part that is not open source is how we build and scale our infrastructure. We build on the AWS cloud and we scale horizontally through sharding. A shard contains everything that's needed to host several conferences. It contains all the signaling components and at least 2 SFUs. We autoscale the SFUs if a shard happens to have a lot of traffic. We deploy on several AWS regions. We have shards in North Virginia, Oregon, Ireland, Frankfurt, Australia. I think that's it. The signaling components are a single point of failure for a shard, so each region has several shards for failover. Other than the shards, each region has an autoscaling group of turn servers in case direct connect fails. And lastly, our SFUs and turn servers run on dedicated C4X larges, which have 4 vCPUs, 8 GB of RAM, and high network performance. Our service has been steadily growing. We have actually doubled in traffic since last year, and we've had our best week ever last week. So here's a few numbers about our service. This past month we did a little more than 91,000 conferences, or about 3,000 calls per day on average. A little bit more during the week, a little bit less during the weekend. The average duration of a call on our service is about 38 minutes, and the average size of a call is 3.3 participants. In total we did almost 3.5 million conferencing minutes, or 7.25 million participant minutes. The average RTT in our service is just slightly below 300 milliseconds, and the average upload bitrate is 1.1 megabits per second, and the average download bitrate is 500 kilobits per second. So this is asymmetric, and the asymmetry can be attributed to two things. First thing is the conferencing features such as simulcast, where participants can upload 1.1 megabits per second. So in that case, with simulcast you stream 180p stream, 180p stream and a 360p stream, but receivers only get part of that, 1.1 megabits per second, because the bridge forwards only one of the two streams depending on the layout. And another contributing factor can be that participants joining or going in audio only mode. In other words, participants are sending video, but there are endpoints in audio only mode, so they're not receiving video at all. We will actually break down and talk more about these metrics later on in this presentation in the results section. So now that I've presented to you the project and the service that this study took place, we are ready to talk about peer-to-peer for one-on-one calls. I'm also going to briefly talk about some closely related concepts, such as congestion control for real-time media, which is the very reason why we need to treat these two use cases differently, and also because it directly impacts the quality of service metrics that we are going to see in the next slides. We are also going to see who else is implementing peer-to-peer for one-to-one, and lastly we'll go over our implementation. So congestion control is a very broad topic with 40 years of research behind it. In this presentation I'm going to severely limit myself in just one slide and talk about the main mechanisms that is used in WebRTC, and I'm hoping I can motivate the need for conferencing features such as simulcast and last N, and thus show why one-on-one calls need to be treated differently than group calls. Currently there are several congestion control algorithm proposals in the RMCAT working group in the IDF, but the most widely deployed algorithm and what we implement in our SFU is the Google Congestion Control Algorithm, or GCC in short. The GCC is a feedback control algorithm. It's split into two parts, an AIMD that reacts to loss and a part that reacts to packet delay variation. So the main idea of the second part is that when the packet delay variation is positive, the network queue is filling up, and thus the bitrate needs to be reduced. And when the packet delay variation is negative, the network queue is being emptied, so we can ramp up the bitrate. So we have noticed that Google is experimented with BBR for WebRTC. BBR is a new TCP congestion control algorithm. It was designed by Google and it's being adapted again by Google for real-time media. This measurement study, however, is based on the GCC. As we can see in the slide, the receiver is sending back to the sender packet arrival times and packet loss information, which are being processed to compute the packet delay variation, and that's in turn fed back to the GCC running at the sender, which produces a bandwidth estimate, and the sender changes its target bitrate to match the estimated bandwidth. This is obviously a very simplified overview of what's actually happening. Depending on the network conditions, the sender may decide to use some bandwidth for packet protection. For example, it may decide to enable forward error protection or spend some bytes on full packet retransmission over the RTX stream. So not all of the available bandwidth estimate goes to media bitrate. Just a final note for this slide, the GCC is implemented both in the browser and in the Jitsi Videobridge. So I've shown you the first drawing in the previous slide. The sender adapts its bitrate based on the bandwidth estimation, but the bridge doesn't do any transcoding, and this is where the conferencing features such as simulcast and last end become crucial. Again, with simulcast, the sender can send multiple qualities of the same video stream, and the bridge chooses which one to forward towards a specific receiver. The specific qualities are currently sort of hard-coded inside the WebRTC engine, but there is standardization work in progress to make this more flexible and more configurable. This forces the sender to send more bits. Simulcast forces the sender to send more bits, and so it's wasteful and costly unless we're in a group call. And furthermore, conferencing features in one-on-one calls are detrimental for user experience, as we will see this later in the results section. And we will see exactly by how much and how it makes things worse. So in order for a service provider to be optimal, it has to distinguish between the two cases and dynamically and transparently switch between them depending on the number of participants in a call. Just a final note on this slide, and only for completeness, others have already shown that a stable group call experience requires the use of a media server, because a peer-to-peer mesh setup has issues with congestion control and bandwidth usage. We provide some references in our paper to support this claim. So, who implements what? Google publicly announced peer-to-peer for one-to-one in 2016. We've publicly released it about a year later in 2017, and Slack mentioned it during ComCon in London a few months ago. So we don't know what the situation is with Skype, FaceTime, or Facebook video, but as we will see, the benefits of using peer-to-peer for one-to-one are quite significant. So if they do not already have some sort of mechanism that for peer-to-peer, we suspect they will implement something in the future. So our implementation, in this diagram, we see the two participants and the bridge. The participants join a call in group mode, which has its own dedicated peer connection, and they maintain the group call peer connection at all times. The group call peer connection is with the solid black line, and it connects the participants with the bridge. If at any time the number of participants drops down to 2 for more than 5 seconds, then the call enters in the one-on-one mode. What this means is simulcast is disabled, last end is disabled, and media is sent received through a new dedicated peer connection. We accomplish this in 4 steps. First, we create a one-to-one mode peer connection. Then the one-to-one mode peer connection attempts direct peer-to-peer connect, and if that fails, it connects via turn. Once that's done, we replace the audio-video tracks in the audio-video elements. And finally, we pose a group call connection media by setting the media direction to inactive. If at any time there are more than 2 participants in the call, we go back to group call mode. So first we resume the audio-video media of the group call mode peer connection by setting the direction to send receive. Then we replace the audio-video tracks in the audio-video elements. And finally we tear down the one-on-one mode connection. We have gathered several types of measurements for the two periods before and after we enable the peer-to-peer for one-to-one extension on meet.jit.si, and the presentation in the presentation we will refer to those two periods as pre and post peer-to-peer for one-to-one. Each period lasted 2 weeks and allowed us to gather representative amounts of data. For the server side, we are using Datadog for monitoring and data collection, and for the client side, we are using the WebRTC stats API, and we forward these stats to Splunk. We are querying the stats at 1 second interval, and then the stats that we're pushing to Splunk are averaged over a window of 15 seconds. We've taken special care to correctly compute the end-to-end RTT if a call goes through the bridge, because you have to compute the RTT in one leg of the connection between a sender and a participant and the bridge, and the RTT in the other leg of the connection between the other participant and the bridge, and then sum the two together. So here's what it looks like. In the pre-peer-to-peer for one-to-one mode period, we've had a bit over than 23,000 conferences, producing a little less than 700,000 conferencing minutes. That's not much. There's not much change in the post peer-to-peer for one-to-one period. We have about 0.5% less conferences and 1% more conferencing minutes. So we didn't have to apply any normalization for the results, which allowed a direct comparison. 77.8% of the conferencing time was spent in one-on-one calls, 12.2% in three-way calls, and the rest is four-way or more. So in this graph, the blue and the green bars represent the pre and post peer-to-peer for one-to-one periods respectively, and we have plotted the downstream, upstream, and combined data transfer. So as we can see, downstream data were reduced by 49%, upstream data by 55%. The combined transfer data were reduced by 52%. Note that in the previous slide we've seen that we spent almost 78% of the time in one-on-one calls. The reason why we do not observe 78% reduced transfer data is because a direct connection is not always possible, so we have a certain percentage of one-on-one calls going through the backend. Like in the previous graphs, the blue and the green bars represent the pre and post peer-to-peer for one-to-one periods respectively. The SFU I/O has been reduced, significantly reduced. We observe 35% less memory usage and 32% less CPU usage, and the system load has been reduced by 46%. Now we will examine some quality of service metrics. In this graph, the blue line represents the cumulative distribution of the end-to-end RTT for direct connect users, and the green line represents the end-to-end RTT for relayed calls, and this includes calls that go through turn and the SFU. The dashed lines represent the averages that we will see in the next slide. So yeah, this specific graph depicts the situation in North Virginia. Since we're interested in observing the improvement caused by Direct Connect, we have grouped the results by region, and we have excluded calls with cross-region participants. In other words, calls with participants from different regions. We've also excluded calls with participants that connect via TCP, because TCP runs its own congestion control and would distort the data. As we can see, direct connect calls have consistently shorter round-trip times, and then in the next slide we will see the averages for the different regions. So here we see the average end-to-end RTT for North Virginia and Ireland. We were unable to collect representative amount of data for Oregon and Australia, so we haven't included those regions in our study. Direct connect calls experience between 22% and 30% shorter RTT than relayed calls, depending on the region. And we can also observe that RTT in Europe is between 16 and 24.6%, depending on the connection mode. So if you're having a peer-to-peer call in Europe, chances are that you will have a pretty short RTT, whereas if you're having a relayed call in the US, chances are that you have a pretty long RTT. Next, we have the upload bitrate cumulative distribution that exhibits a bit more interesting behavior. So here we have split the data in three categories: direct connect in blue, turn relayed in red, and SFU relayed in green. The dashed lines represent the averages that we will see in the next slide. Multiple observations. So a first observation is that the averages are relatively close to each other at around 1.1 megabits per second, which matches our overall service average. A second observation is the lower performance for turn relayed calls, and the more interesting observation is the irregular behavior of the SFU relayed cumulative distribution. There's two things that can explain this. First is the congestion control algorithm that is used. The GCC has had multiple iterations, and the version that is implemented in our bridge does not necessarily match the version used in the endpoints. Second is the use of conferencing features, and more specifically the use of simulcast. We can see that there are some bitrates with high likelihood of occurrence. These are near the simulcast layer minimum bitrates as defined in the WebRTC engine. For example, we see many occurrences of bitrates around 1.2 megabits per second, which is the 720p layer activation threshold. And similarly, we see many occurrences of bitrates around 700 kilobits per second, which is the 360p layer activation threshold. We also notice a spike around 3.2 megabits per second, which is the maximum target bitrate when simulcast is activated. Here we see the download bitrate cumulative distribution for the three categories that we defined in the previous slide. First, we confirm that turn relayed calls have worse performance than direct connect calls. If we focus on the SFU relayed cumulative distribution, we can observe a number of things. First, the average download bitrate is much lower than direct connect and turn relayed calls, despite the fact that SFU relayed calls have higher average upload bitrate. This actually reduces the throughput efficiency of SFU relayed calls. We will see by how much exactly in the next slide. We can also observe a few bumps in the graph. For example, we see a bump at around 2.5 megabits per second, which is the maximum bitrate for the 720p at 30 fps layer. We can also observe that most bitrates fall under 700 kilobits per second, which is the maximum bitrate for the 360p layer threshold. This is because even though the sender is probed for additional bandwidth, they're not able to activate the 720p at 30 fps resolution layer. So here is the summary of all this. In this slide we can see the average download bitrate over the upload bitrate in the different regions and for the different connection modes. There's some measurement noise, and so while we would expect the turn relayed calls and direct calls to have exactly the same upload and download bitrate values, they're not exactly the same, but within a 4% error at most. Turn relayed calls in the US achieve somewhat lower performance than in Europe. The important observation is that the reduced efficiency of SFU relayed calls, which makes imperative and clear the need to disable conferencing features for one-on-one calls. SFU calls achieve 60% efficiency in Europe and 52% efficiency in the US. So to sum up, peer-to-peer for one-to-one can save you lots of bandwidth. In our service, our combined data transfer was reduced by 52%. It can reduce the infrastructure pressure between 35 and 40% in our case, and it can also improve the quality of service of your calls. The RTT was reduced between 20% and 30% depending on the region in our service. Also, turn and direct connect calls have about the same throughput, and one should at least make sure to disable conferencing features for one-on-one calls, as they are wasteful and and cause low efficiency for one-on-one calls. Thank you very much, and please feel free to ask me questions at this point. Thank you.